Our general model of our wireless, of any system, wireless system, is that we have a transmitter. We take some electrical current from, say, a computer that just want to transmit some data, and the antenna converts that electrical current into a wave, an electromagnetic wave, the signal that we're sending from A to B. And the receiver antenna takes that waveform and converts it back to electricity, which is then received by our receiving computer. So we care about the antennas, how they're designed, what are their characteristics, and another thing we'll go through today is look at the relationship between the antennas, the power of transmitting and receiving, and the distance. How far apart can we place our antennas, our transmitter and receiver, so that they can still communicate? The antennas. We said yesterday an ideal antenna is an isotropic antenna, where if we transmit our signal out of an isotropic antenna, it disperses equally in all directions. So we can say that we start with a power level that we transmit, and that power, the energy, disperses in all directions. How do we measure power? What are the units? Watts, okay? Watts. Remember, when we talk, we can talk about volts, but when we talk about communication systems, we'll usually talk about, use the units of watts. 1 watt, 1 megawatt, 1 microwatt, and so on. Okay, so when I talk about a signal strength, the signal magnitude, the signal power, I mean measured in watts. So with an isotropic antenna, I transmit some power out of the antenna, and we say that we start with the transmit power, say PT, some power we start with, and that energy disperses. And one factor that we know about is attenuation. As that signal travels across a distance, it will get weaker and weaker. And today we'll cover and see how much weaker. So if this is my transmitter, I transmit with some power level, say 1 watt. The energy comes out. If this is an isotropic antenna, the energy goes in all directions. And at some distance ahead, if I measure the power at that point, it will be less than 1 watt. Because if it comes out at 1 watt, it gets weaker across distance, so it's going to be less than 1 watt. We want to see the relationship between what impact the antenna shapes have on the dispersion of the energy, on the power, and also eventually how much weaker does the power get across some distance. We'll do that today. Isotropic, think of some ideal or theoretical antenna. The antennas that we use actually concentrate some power in a particular direction. So they don't disperse the power equally. There may be some concentration of energy in one direction, so it's strong in one direction, but weak in some other direction. And we said there's an omnidirectional antenna, which tries to be equal power dispersion in one horizontal plane, for example, but up and down in the vertical plane it may be weaker. And more generally, a directional antenna, which tries to send the energy all in one direction and very little in the other directions, so that the signal goes much stronger in that one direction. Now, the first important thing we want to introduce today is how do we measure these directional antennas, an omnidirectional antenna, and how can we talk about how much greater or how strong the signal is? Well, everything is done relative to this ideal isotropic antenna. And the handout, we'll use this extra handout. If you don't have one, there's a few copies lying around. Just a few pictures to try and demonstrate this concept of real antennas, which have some directionality, versus the isotropic antenna. Of course, I cannot draw very well in 3D, so I'm just going to draw in a 2D picture of our antenna. So imagine just looking at one plane, say a horizontal plane. Let's say I've got an isotropic antenna at this black dot, and I transmit a signal with some power level called PT. And let's write down and give it a number. In this handout, I'll just use variables. But on the board, let's say, for example, I just make up a value. I transmit a signal with some power level, PT, equal to 4 watts, as an example. So I think that's the power that I start with, 4 watts. If I use an isotropic antenna, from all directions around that antenna, the signal goes and disperses equally. So if I had a device that could measure the power level, say 1 meter away, I walked 1 meter away from the transmit antenna, and I measure the receive power, is it going to be greater or less than 4 watts? That's the first question. Is it greater, same, or less than 4 watts? I measure at this point, 1 meter away from the transmitter. It's going to be less than 4 watts, okay? Because we know, because of attenuation, if we start with 4 watts, across some distance the signal gets weaker. So remember that. It always will be less than 4 watts. How much, we don't know, but it will be less. Now, if I measure the receive power 1 meter away in this direction, and let's make up a number, I measure it to be, say, PR to be 1 watt. Okay? I measure it to be 1 watt. And then I go and measure 1 meter away in the opposite direction. What's the power level? It will also be 1 watt. In all of these positions 1 meter away from our isotropic antenna, because an isotropic antenna disperses the power equally in all directions, if it's 1 watt 1 meter away here, then 1 meter away here will also be 1 watt, and 1 watt here, and so on. So if we take this distance of 1 meter away from the transmitter and measure, it will always be 1 watt. In this example, I'm not saying that in all cases 1 meter away goes from 4 to 1. I'm just using these numbers as an example. If I measured the power 2 meters away, will it be less than, equal to, or greater than 1 watt? It'll be less than, okay? The further we go away, the weaker it gets. That's just attenuation. So isotropic, equal in all directions. Let's say now I have a real antenna which is not isotropic. It focuses the energy in one particular direction. And I buy this antenna, the blue one, and I put it in the same position as in my isotropic antenna, the blue dot here. What this blue shape or the line shows us is that, or go back, what the circle shows us, if we take the received power and if it's 1 watt, then we plot a point on the circle, or we get a point of the circle. What the blue one shows us is that if I measured at this point, I get a received power of 1 watt. If I measure, which may be, I don't know, 3 meters or 2 meters away, if I measure at this point on the blue line, I'm saying the received power is also 1 watt, and at this point 1 watt, and at all points that I measure the signal on that blue line, let's say we measure it to be 1 watt. The same with the circle. I'm saying at all points on that circle, if I measure the signal, if I get 1 watt, 1 watt received power. With isotropic, we get the circle. With my directional antenna, we notice that the power is concentrated in one direction. And in fact, in the opposite direction, this way, it's in fact weaker. So let's analyse that a bit more. So we're saying that, say, at this point, the received power would be 1 watt. The same as if we used an isotropic antenna and measured at this point. What if, using my blue antenna, I measure the power here? What's its value? Anyone want to guess or say something about the value? If I measure at this red dot the received power from my blue directional antenna, what can you say about the power level? Not 1 watt. Let's make notes. This is my isotropic. In both cases, we start with the same transmit power, 4 watts. I'm saying 1 metre away with isotropic in any direction, we measure to be 1 watt. With my directional antenna, my example antenna, the transmit power, again, is 4 watts. I just made up that number. And what we're saying this blue line represents, at every position on that blue line, the received power is again 1 watt. Now, and of course this is on a geographical map, that is the distance between the transmitter and this point is greater than from this point to here. So, what can we say about px? It's less than 4 watts and it's more than 1 watt. Okay? We cannot say any more the exact value, we don't know yet. But of course it will be less than the transmit power because again our signal attenuates across distance. It's got to be less than 4 watts. But in this direction we notice if we start at 4, we've said that this point further away we have 1 watt. That means if we measure px, because it goes down, it must be greater than 1 watt. Px is greater than 1 watt and less than 4 watts. Somewhere in between. I don't know the value. Let's give it a number. Okay, let's say we did measure the value and found px to be 2 watts. Okay. Now, compare from that point. If I use an isotropic antenna and measure the signal at this point, what power level? 1 watt. Okay, from our isotropic, if I measure the signal at this point, I get 1 watt. If I use my new blue directional antenna, what power level at this same point? I've said px 2 watts. How much stronger? Twice as strong. So we can say using my directional antenna, the signal strength some distance away is twice as strong. We've got 2 watts divided by the original 1 watt. So this was for isotropic, 1 metre away, and this was for my directional antenna, 1 metre away. The 2 power levels measured. We can say the gain of using my isotropic antenna relative to using the gain of using my directional antenna relative to using an ideal isotropic antenna is 2. Our signal is 2 times stronger. In that direction only in this direction. If I looked at the opposite direction, it would be different. This is antenna gain. And it's a common characteristic when you see an antenna or purchase an antenna, one of the properties in the specification will be the gain, which says that a gain of 2 says that this specific directional antenna in this one direction will have a power 2 times as strong as if you used an isotropic antenna. What if, using my directional antenna, I measure the power here? What can we say about, say, the px at this point? Any observations? If we measured with the blue one at this point, what would the power level be? It will be less than 1. That's the thing we observe. Because this blue line says if we transmit here at 4, at this point we'd get 1 watt. That's the definition of this blue line. Therefore, further away it will be less than 1 watt. So if we took at this point, then with the directional antenna, let's say it was less than 1, it was half a watt, 0.5. Then the gain would be 0.5 divided by 1, would be half. In fact, it's not a gain, it's a loss. A gain of a half is a loss by a factor of 2. We've halved the power. That is, with a directional antenna, in one specific direction we may have a high gain, but in other directions we may have low gains, which is always the case. With antennas, when you look at the details of them, you'll often see plots, some pictures that look like this, that try and illustrate that in one direction the gain is high, but in other directions it's low. They're drawn slightly different than this, but try to capture the same information. And another characteristic, we often are interested just in the largest gain. So with this blue antenna, think of it, if I point it in this direction, I get high gain, a gain of 2. But if I point it in this direction and measure in that direction, I get a low gain. So behind it it's not good, but in front it's good. A common property that you will see with antennas is what is the highest gain that this antenna can achieve, which is in the direction where we get the highest value. In this example, in this direction. So, with our blue antenna, I can calculate with this example the gain is 2. It's 2 times stronger than an isotropic antenna. We can also express gain not just as a factor but using decibels. Remember decibels? Decibels is 10 log 1 power level divided by another power level. Well, we have 1 power level divided by the other. The other is the power for an isotropic antenna. So in decibels, we get 10 log base 10 of 2, which is log of 2 is 0.3 times 10 is 3 dB. And the notation we use with antenna gains is that my directional antenna is 2 times stronger than using an ideal isotropic antenna. Or in decibels, 3 dB. And to indicate this 3 dB is relative to an isotropic antenna, we add an I, lowercase I here, and we get dBi. What it means is, so 3 dBi means 3 dB greater than using an isotropic antenna. And that's a common characteristic of antennas. Yep.
If we add more point on this, for example, if I add PZ or PY here, and it will be equal to PX?
No. PX, the one that we calculated, which gave us a gain of 2 watts, was only for this specific direction. Because this blue antenna is designed to focus the energy in one direction. So you can imagine that most of the energy goes in this direction. Some of it goes in this direction. Very little goes in this direction. That's what this blue shape is showing. So we have a high gain in this direction, slightly lower gain in this direction, and then it gets lower and lower, and it's quite a small gain in this direction, like less than 1. So it will vary depending upon the location. But often we care just about, well, what is the highest? What's the best we can do? From this website, and I didn't get to show you yesterday, the internet wasn't working. You'll find some links to this page eventually, and I've scrolled down a lot, but just quickly, it lists some products that this company sells, some antennas. So this is one of those antennas like on the access point, these small dipole antennas. There's a mount here, and it's just that stick-style antenna. It shows, where's my pointer? It captures, based on the design of this antenna, information about the gain in different directions. That's what these two plots do. We'll not explain how they are interpreted, but similar to mine, but in a slightly different style. It looks at the azimuth and elevations. So in one plane, the horizontal plane, and in the vertical plane, how much gain in particular directions. So it's equal or approximately equal in all directions on the horizontal plane, but if you go up and down, these are angles, we see that it's strong, say in this area, but as you go higher it gets very weak. So this is some way to capture the gain of this specific antenna. The greatest gain is given here as part of the spec. 2.2 dBi. So if you buy this antenna, the best you can achieve is 2.2 dBi if you point it in the right direction, which means 2.2 dB better than using an isotropic antenna, a bit less than the one we used in our example. And there are other antennas. I'll just scroll through. Now, similar. Let's find a 5 dBi sector antenna. 5 dBi is the maximum gain of this antenna, so you mount it on a wall, for example, and it points out in one specific direction. So you can think on the horizontal plane, if the antenna's here, it's strong in this direction but weak in the reverse direction. So that's what these diagrams try to capture. But maximum 5.5 dBi. And just quickly, a ceiling mount antenna, a wall mount antenna, 6 dBi. Slightly different patterns. So depending on what area you want to cover, you choose the antenna which will give the signal strongest in that area. If you want to cover, I don't know why, but if you want a wireless access point to cover just this straight down here but not in the corners. So if you use your laptop in this area you can access, but here the signal is very weak. Then you'd buy an antenna and mount it here, and you'd choose one which has a pattern such that the signal goes strongest in these areas and it's weak in these areas. So depending on what coverage you want, choose the antenna pattern. 8 dBi, 10 dBi, so different style antennas. 13 dBi and so on. So they list some of their products there. So each antenna we can characterize and calculate its, or determine its gain. Let's ignore the physics of parabolic antennas. We'll come back to them in a moment. Well, how can we calculate the gain? All right, we can do measurements. That is, if I have an isotropic antenna and measure 1 meter away, and then take my real antenna and measure 1 meter away, then I can calculate the gain. Okay, so we can do that. can we calculate it some way without measuring? Well, yes. Here's a general formula. The gain G of an antenna is 4 times pi times by the effective area of that antenna divided by the lambda, the wavelength squared. So first, the wavelength. The gain depends upon the signal that we're sending. What's the equation for wavelength? Very important one. Lambda, wavelength, speed of light divided by the frequency. So remember the relationship. The speed of light is fixed, c, 3 by 10 to the 8 meters per second, divided by a frequency of our signal. So if I know the frequency of the signal that I'm using, let's say 5 gigahertz is the signal I'm using, I can determine the wavelength, lambda, and use that in this equation. So the gain of an antenna depends upon the signal we're transmitting with that antenna, the frequency or the wavelength of that signal. And it also depends upon the effective area. What is the effective area? Well, that's related to the physical size. Generally, the bigger the antenna, the bigger the effective area. But it differs amongst different antenna designs, whether it's a dipole antenna, whether it's a sector or patch antenna, or whether it's a parabolic dish antenna. They have different effective areas. For this course, we will not explain or look any more details about the effective area. In some questions, I may say the effective area of this antenna is X. Okay, I would give that to you. Or I would say that the effective area of a parabolic antenna is half of its physical area, as an example. What's a parabolic antenna? One of those dish-shaped antennas, like in here, if we look at a side cut of it. Like if you have satellite TV, the receiving antenna is a parabolic dish antenna. What's the approximate area of a parabolic antenna? How would you determine it? Approximately. If you look, you know the antennas I'm talking about, the dish-shaped antennas. If you look at one, looking down on it, what's it look like? So here's my dish antenna. It's curved like that. If you looking down on it, what shape is it? It's a circle. Okay, from that dimension, it looks like a circle. So what's the size or the area of that parabolic dish? It's about the size or the area of a circle. So if we know the size of the antenna, let's say it has a radius of 1 meter, which is quite big, radius of 1 meter, then we can calculate the area or the approximate area of that antenna, pi r squared. And then we'd say, okay, once we know the physical area, well, the effective area is, say, half of the physical area. What is this multiplier? In fact, differs in some cases, but as an example, a half of the physical area. Once we know the effective area, we know AE. If we know the wavelength of the signal we're sending with this antenna, lambda, we can calculate the gain of that antenna, G. Where the gain is the absolute value, like this. It's not in dBi. Okay? If we want it in dBi, we need to then convert. This equation gives us this value, not the value in dBi. Think of different units or different scales. A quick example. And we'll use this example later. So, let's say we have a dish antenna. So I have a dish. and it's 1 metre diameter. What's the area of that dish, approximately? Or how would I calculate the area of this parabolic dish antenna? What is it? Calculate the area of a circle. No, not 2 pi. Pi r squared. What's the radius? Well, our diameter is 1 metre. The radius is half a metre. Half squared. So there's our approximate area of this parabolic dish antenna. A 1 metre, which is what, about this size antenna, a dish shaped, has an approximate area of about 1/4 pi square metres. And let's make an assumption and say that the effective area is half of that. I'd have to give you that in an exam, this assumption, but let's say the effective area, AE, is a half of the real area. And then we get, you do the maths, pi on 8 metres squared. So with this 1 metre diameter dish, the effective area is about pi on 8 square metres. Pi 3.14 divided by 8, so a bit less than half a square metre. Now we send a signal using this antenna. Let's say we know the frequency of that signal. It's 5 gigahertz. Find the gain of our antenna. Quickly try and find the answer. Some very simple maths. We know the frequency, we know the effective area, find the gain. Of course, using this equation, 4 times pi times the effective area divided by lambda squared. What's our wavelength? Anyone calculated the wavelength yet? Remember, frequency of 5 gigahertz, speed of light, 300 million meters per second. Three by 10 to the 8. Giga. 10 to the power of 9, and you can calculate is 0.06 meters. Our wavelength. And now just plug in the values into our gain equation. We know the effective area, we know the wavelength. Find G, and so we can move along because I calculated it in the previous class. I'll give the answer. It's about 1371. $1370 point something. Okay, you can use your calculator to solve that. It's 4 times pi times our effective area of pi over 8 divided by 0.06 squared. So as long as you get the units correct, meters, meters squared for our area, then you'll get the right answer there. No units. What that tells us is that my dish antenna of a parabolic dish of 1 meter in diameter, if I measure the signal when I use this dish antenna and then measure it again at the same distance away using an isotropic antenna, using my dish antenna, the power is 1,371 times stronger than if using isotropic antenna. So that's the gain, 1,371 times stronger. Convert it to dBi. So this is the absolute value, not in decibels. Now convert it to dBi. And with a calculator, I've done it before, and it is about 31 dBi. Simply log of our gain multiplied by 10. So most antennas in practice you will see the gain expressed in dBi, but we can convert it back to the absolute value if needed. Remember, decibels is not a unit, it's a logarithmic scale. That is, it compares one power level to another. The general formula, 10 log power 1 divided by power 2. A ratio of 2 power levels. Well, in our case, our ratio is 1,371. 1,371 times larger than using isotropic. So 31 dB larger than isotropic. To indicate that we mean larger than an isotropic antenna, we include the I here, meaning isotropic. Any questions before we move on to the next concept? So when you go out next to buy an antenna, you'll look on the spec and you'll see and notice, well, which one's stronger based upon the gain, and it will be a part of the spec saying 2 dBi, 5 dBi or whatever. To get more details about where is a signal strong for that particular antenna, you need to look at those plots that show, is it strong in elevation, in azimuth, or which direction. So we know something about antennas and how strong they are, or how we can measure their strength, particularly the gain. Let's now look at how signals propagate through the air. We know that they attenuate. We know that when we transmit, they get weaker across distance. Shortly, we'll see an equation to determine, in some conditions, how to calculate how much weaker they get. Because it's important to know, if I start with a transmit power of 4 watts and I transmit for 1 meter, what's the receive power going to be? Is it going to be 1 watt or something else? Well, we'll see a way to determine that shortly. But first, let's look at some general characteristics of different frequency signals. How do signals propagate? Wireless signals. Well, it depends upon the frequency that we use. The first classification we see, we divide into 3 different types of propagation. If we're sending signals with frequencies below 2 megahertz, we talk about what's called ground wave propagation. The signal follows the contour of the Earth. These plots show those concepts better. They go together, those 2 slides. The top plot shows, of course, the Earth. It's curved if we look at the entire Earth. If we have a transmitter and a receiver, if we're sending signals less than 2 megahertz, then the signal follows the contour of the Earth. So it can go around the Earth, in theory. I cannot remember the physics of why that happens. You can go back and look at high school physics and read the textbook and talk about what causes both ground wave and the second one, skywave propagation, of how signals of different frequencies bounce off things, reflection, refraction, and so on, how they are affected by different molecules, water and so on, and how that determines the direction that they take. It's interesting to read, but we're not going to cover it. We just need to understand, well, given different frequencies, what are the characteristics of the propagation? Ground wave propagation, follow around the Earth. Skywave propagation, if we're using between 2 and 30 megahertz, effectively bounces off the ionosphere and the Earth. So we send a signal up, it bounces back down to Earth and up, and again we can use this technique to send the signal around the Earth, from Thailand to somewhere in Europe. We don't have a direct line between them, a line of sight we'll see in the last one, but using the first 2 techniques, if we use the right frequencies, we can have that signal go around the curvature of the Earth. The last set is anything above around 30 megahertz. We have what's called line of sight, LOS propagation. The signal goes straight, which means to be able to receive it, we need no obstructions between it. If we're using line of sight propagation, if I have an antenna here in Thailand and a receiver in Europe, they will not be able to communicate, because there's not line of sight between them. There's the curvature of the Earth, which is the obstruction in that case. But with the first 2 approaches, we would be able to communicate. Turns out most of the systems we deal with today use line of sight propagation, greater than 30 megahertz. There are some special cases that use these. You think of what's called shortwave radio. You can get radio receivers that will pick up radio stations from anywhere in the world. So from Europe, from the US, they use a shortwave radio which follows the contour of the Earth to be received by your radio. It's one case that you may have come across. So depending upon the frequency of our signal, the signal propagates in different manners. This table captures a more detailed range of frequencies and some typical uses of signals at those frequencies, some example applications, and the propagation characteristics. And it's divided by these bands that we introduced yesterday, like low frequency, ultra high frequency, infrared, and visible light. Let's just look at a few selected examples. Infrared. Your remote control for your TV. You are sitting in your lounge room. Your TV's in your lounge room. You're sitting in your bedroom. You want to change the channel, can you? TV's in one room, you're in another room. Can you change the channel with your remote control? Unlikely, okay? Because your remote control uses infrared, most normal ones do. Frequencies ranging, as listed here, up to terahertz. And the characteristics of signals at these frequencies is that they use line of sight propagation, they need to be direct, and B, that the signal comes out of your remote control and it hits a wall, and the wall has materials that obstruct that signal. It doesn't pass through the wall. Okay? Light does not pass through walls. So, as a result, the signal cannot be received at someone on the other side of the wall. Now, you have your laptop in your bedroom at home and you have the wireless access point or router in another room. Can you use the wireless internet? Yes, I think some of you would have done it. You have here, I have an access point here, maybe I'm out in the corridor. There's a wall separating me, my wireless transmitter, the laptop, and the wireless receiver. Can they communicate? In many cases, yes. Because wireless LAN uses a different frequency range. It's in the order of 2.4 gigahertz, which falls in here, ultra high frequency. Again, uses line of sight propagation, but the characteristics of those lower frequencies is such that the frequency or the signal will go through the wall. It hits the materials in the wall and is attenuated by the wall. It gets weaker, but some of the energy passes through. So depending upon the frequencies, we can pass through obstacles in different manners. And that makes the selection of the frequency important depending upon your application. Satellite TV. Again, going back to your dish antenna at home, you receive a signal from a satellite up in space. The signal most likely will not go through the building. You usually need your antenna, your receiver antenna, to be pointed at the satellite. If you're on the wrong side of the building and you do not have line of sight to that satellite, you probably will not be able to receive satellite TV. In some cases, in some systems with satellite TV, which uses frequencies in the order of, in this super high frequency range or band, in the order of 10 gigahertz, frequencies in this range are attenuated by the atmosphere and water vapor, for example. So when it's raining, the signal from the satellite comes down to your home and the receiver, and the signal needs to go through the rain, the water in the atmosphere. But when it hits that water, the signal gets weaker, it attenuates. So if it's raining a lot and the signal goes through, it may be that the signal received is very, very weak. And on your TV, you may see some disruption or some poor quality signal, poor quality image, because the satellite signal at those frequencies is attenuated by water vapor in that case. So depending upon the frequency, we need to consider the environment, where we need to send the signal, and how far we want to send to determine what's a good frequency to use. So this just gives a set of examples of different systems. The last thing we want to do today, or the main thing, is come back to this issue. I transmit a signal, we know it attenuates, it gets weaker across distance. The question is, how much weaker? I had an example at the start that said I transmitted with 4 watts. Across a distance of 1 metre, I received with 1 watt. Well, I made that number up. I'd like to be able to determine over a distance of 1 metre how much weaker is the received signal compared to the transmit signal. We know our signal loses power across distance. How much power does it lose? Well, there are models, mathematical models to determine that. It's called path loss. Across some path, I lose power. And the one we'll cover is called free space loss or free space path loss. So it talks about, or it gives us a model for determining how much power we lose across some distance. The signal attenuates over distance, it gets weaker. That's one impairment, and the only one we will cover in this course. There are other impairments, like I mentioned with satellite. If the signal passes through water, it attenuates, or if it tries to pass through a wall, the signal gets much weaker, and we may or may not be able to receive on the other side. Depends upon the frequencies and the materials that it needs to pass through. In some cases, there's things called multipath, where signals bounce off walls and multiple copies of that signal arrive at the receiver. That creates problems. We're not going to explain or go into any detail of these three. Let's focus on how much power do we lose between transmitter and receiver. And let's give a mathematical model for determining how much power we lose. It's called the free space loss model, or a free space path loss model is another name. The free space part assumes that we're operating out in space, in free space. Well, maybe more accurately, in a vacuum. There is no other transmissions. Assuming there's no other transmissions, there's no obstructions between transmitter and receiver. If I start with some power level, how much power do I lose across some distance d? This equation gives us that relationship. So it's an ideal model. It's not true inside this building and in most practical cases, but it's a good approximation or a good way to start with determining path loss. Let's look at the different variables. We start with some power level. We transmit with some power level PT. We transmit our signal across some distance d. And the signal has some wavelength lambda, and from that some frequency. There are two antennas involved in the transmission, the transmit antenna and the receive antenna, and both have some gain, GT and GR. And we receive some power, so the signal received has power PR. So all these factors come together. So if we know all but one, we can determine that one. So this assumes there are no obstacles between transmitter and receiver, and we're operating in a vacuum, no other transmissions, and perfect antennas. So just determined by their gain. Let's go through an example to illustrate how we can use this mathematical model of path loss. Let's try and first illustrate a scenario where we have a transmitter and receiver, and we want to determine some characteristics of the system. What if we start with? We have our transmitter, an antenna, and we have our receiver, an antenna, and they're separated by some distance d. So let's note d. So the distance between transmit and receive is d meters. We're going to send a signal which has some wavelength and frequency. So the wavelength lambda we'll need to know. That's lambda, or the frequency. From the frequency we can determine the wavelength. The free space loss model tells us the relationship between these two factors, and if we start, we transmit a signal with some power level, PT. If our transmit antenna has some gain, GT, our signal comes out of the transmit antenna. We start with PT. The transmit antenna introduces some gain, increases the signal. The signal comes out of the transmit antenna, and it gets weaker as it goes across the d meters. Then it's received by the receive antenna, which also has some gain, I'll write that in a moment, which increases the antenna. The resulting power level is the receive power, PR. So this equation relates all those factors together. So the receive antenna has a gain, GR, and we receive with a power PR. Let's give some numbers so we can do a quick calculation. Let's say I have a system and we have a distance of 1 kilometre. We have a transmit power of 1 watt. The gains of our two antennas are the same as what we calculated in the previous example. What do we get? So that 1 metre parabolic dish antenna, we calculated a gain of 1371 GT. And in this example only, let's say that both antennas are the same. They don't have to be. One can be a big antenna, one can be very small. But in this example, they're the same antennas and therefore the same gain. GT, GR 1371. And we had in the previous example a wavelength of 0.06 metres. Metres, that is. There's our scenario. If I want to transmit a signal across 1 kilometre using these two antennas and the gains of those two antennas, using a wavelength of that signal of 0.06 metres, a frequency of 5 gigahertz, if I transmit with power 1 watt, my signal comes out, it gets weaker. At what power is it received with? What is PR? Find the answer. Find PR. And you use the free space loss model equation. And this is the example in the handouts. That is, use this equation to solve this question. It's very easy because you have the equation, you just need to rearrange it so you can calculate PR, because all the other variables are known. If you rearrange, if you could look at the slide, you get PR is the transmit power, PT, times by the two gains, GT, GR, times by, is it lambda squared, divide by, what do we get at the end? 4 pi d all squared. All I've done, I take this equation and rearranged it to find PR. And a quick rearrangement gives us this. Transmit power times by the two gains times by the wavelength squared divided by 4 times pi times the distance all squared. Anyone have an answer? The hardest thing now is just to make sure that you use the right units. In our case, PT is in watts. This is 1 watt. GT is 1371. Okay, just substitute. GR is also 1371. Lambda is 0.06 meters. 4 times pi times what's d? It's 1,000 meters, okay? Because if we're using the units of meters here with everything else, then we need to make sure d is in meters. So don't use d equal to 1, do d equal to 1,000. And with a calculator you can solve that. Anyone have the answer yet? It's about 42.8 microwatts. Okay. What it tells us. So, all right, you don't have to do the calculation now. In an exam, you'll have your calculator. You can solve that easily. What it tells us is that if I start with a power of 1 watt, I start with, if this is the magnitude of my signal, 1 watt, with these 2 antennas and this 5 gigahertz signal, I transmit a signal out of, well, I start with 1 watt. The antenna introduces some gain, so think that magnifies the amplitude of my signal. Then when it comes out of the transmit antenna, the signal attenuates across the distance, getting weaker and weaker and weaker. It's received by the receive antenna, which introduces some gain, which multiplies it by 1371. The resulting value is the receive power. And in this case, the receive power is quite small compared to the transmit power, 42.8 microwatts. So across this 1 kilometre, we ended up with 42 microwatts. How can we use this? This tells us if I need to buy a receiver, the receiving equipment, usually a characteristic of every receiver is the minimum power at which it can successfully receive. Same as your ears. What's the minimum audio signal that your ears can make sense of? Well, we had an example a couple of weeks ago where if I talk very quietly, you cannot hear me because the signal you receive is very weak. It's too low for your ears to make sense of. Same as our receiver electronics. At our receiver device, we can use this knowledge to work out, well, what's the minimum power that receiver needs to be able to receive? Because we know how much power is lost across this distance of 1 kilometre. So the example was a simple application of this free space path loss model, which tells us how much power do we lose if we're operating in free space, in a vacuum. No obstacles, perfect antennas. In real life, there are obstacles, there is noise, we don't have perfect antennas, perfect devices. There are other models that people have developed to model how much power we lose in different scenarios. For example, inside a city, or for TV transmission across a city, or inside a building. So there are different mathematical models to determine approximately how much power you lose if you start with some transmit power and transmit a signal across some distance with particular antennas and frequency of the signal. But those mathematical models, the ones that I list but don't give the equations, are more complex than this, and they make more assumptions. So we'll not go through them, but just be aware that there are other models. But using this, we can predict approximately how far we can send our signals. if I knew the gain of my antenna in my laptop, the transmit gain, and the gain of the antenna on this access point, GR. If I knew those values, and I can find them out. I think when you buy this access point, it gives you the specification of the gain. It's about 2.2 dBi for those antennas. For the laptop, I think you could find out the gain of the antennas. So if I know GT and GR, I know the wavelength I use with wireless LAN because I know the frequency is 2.4 gigahertz. Therefore, for Wi-Fi, I can determine the wavelength, so I can determine lambda. For this access point, I can determine the transmit power. It's again a part of the specification of the device. I can look it up, and I think from memory, it's normally, one of them is 100 milliwatts. The transmit power of my access point, 100 milliwatts. So if I know GT, GR, lambda, transmit power of my access point is 100 milliwatts. And another characteristic of devices is the minimum receive power. I can look up and find the receive power needed for my laptop to successfully receive a signal. So if I know PR, then in theory what I can use this equation for is to say, okay, I know PR, the PR needed, I know GT, GR, lambda and PT. I can find the maximum distance I can separate the laptop and the access point by such that they still communicate. That is, I can rearrange and find D, the distance, which tells me, I don't know, if the value is 1,000 meters, then it tells me if I separate the access point and laptop by 1,000 meters in free space, not inside a building, but outside with absolutely no obstacles, no interference, then they should be able to communicate. So we can use that for such calculations. It doesn't apply inside a building because there are obstacles and there's other interference. Questions on the free space loss model? You need to apply it in different scenarios. I will not ask you to remember the model, the equation. Okay? In an exam I give you that equation, but you'll often see questions like, here's the scenario, and you need to understand, okay, this is PT, this is GT, GR, this is lambda, and okay, I know the distance, I need to find PR, for example. So usually I give you a question which is, here's the equation, here's some description. From that description you can find all but one of the variables. Then you just rearrange to solve for that one missing variable. Last 10 minutes. Let's finish with something slightly different. Some notation. Some new notation. Remember our general equation for gain. The gain in dB we calculated as 10 log base 10 of one power level divided by another. Where we spoke about gain, we said P out divided by P in. Let's just write it as one power level, P1, generally divided by P2. That's when we have a ratio between two power levels, P1 divided by P2, we can express it in dB by taking the logarithm in base 10 and multiplying by 10. For example, here we had the ratio of two power levels. 2 watts relative to 1 watt gives us a ratio of 2, or expressed in dB, 3 dB. But in this case, the power level of 2 watts was relative to the power level if we used isotropic antenna. So the notation we used in the end was saying that if I have 2 watts with my directional antenna, gives a gain of 2, which is equivalent to a gain of 3 dBi relative to the isotropic antenna. This last letter here, the I, means 3 decibels relative to using isotropic antenna. We can use that same concept with other factors. Let's say, for example, P2 is 1 watt. And P1 is 100 watts. What's the gain? What's the gain from P1 to P2? It's a factor of 100, or in dB, the absolute factor is 100. 100 divided by 1, easy. In dB, it is 20 dB. Log of 100 is 2 times by 10 is 20 dB. Okay, that's our normal. We say P1 is 20 dB larger than P2. Another way to write P1, 20 dB, it's 20 dB larger than 1 watt. So we get this new notation, dBW. P1 is 20 dB larger than 1 watt. The ratio between P1 and P2, or P1 and 1 watt, so think of this as the reference power level, is 100 or 20 dB. So another way to write 100 watts is simply 20 dBW, where the W means the other power level is 1 watt. So now we're using dB to express an actual power level. My input power is 100 watts, is the same as saying my input power is 20 dBW. So now we're using dBW as a different notation. What if I had a power level P1 of 10 kilowatts? What is its value in dBW? I have a power level of 10 kilowatts compared to 1 watt. How many dB? 40 dBW. 10 kilowatts, remember, is 10,000 watts. 10,000 watts relative to 1 watt, and that's what this W means in dBW, is a factor of 10,000. Log of 10,000 is 4 times by 10. 40 dBW. So 10 kilowatts is equal to 40 dBW. So this new notation is relative to some reference power level. In this case, the reference is 1 watt. And it's commonly used in communication systems and other systems. Another reference which is commonly used is not 1 watt, but 1 milliwatt. What if P2 was 1 milliwatt? And P1 was, for example, 100 milliwatts. That's an M. Relative to 1 milliwatt, How many dB is P1 larger? Relative to 1 milliwatt. Or let's make it simple. How many times larger is P1 than P2? 100 times. That is, relative to 1 milliwatt, a power level of 100 milliwatts, this is an M, is 100 times. Expressed in dB is 100, is a factor of 100 is 20 dB. Log of 100 times 10. So we can also write here 100 milliwatts is 20 dB MW. 20 dB relative to 1 milliwatt. And in fact, it's common not to write dB MW, but to omit the W and just write dBm. So when you see dBm, don't think of decibels relative to 1 meter, think of decibels relative to 1 milliwatt. That's the more common notation. Okay, this will test you. If I have a power level of 60 dBm, how many watts? So I say that my system takes an input power of 60 dBm. How many watts? If you can solve it and tell me the answer, you can go home. Try and find the answer.
This is 1 megawatt.
1 megawatt. No. No. Anyone else? Someone said 1 megawatt. Someone's had 1 watt. 1,000 watts. Correct. Remember, dBm is a power level relative to 1 milliwatt. So 60 dBm, and I'll not try and do the calculations here, but 60 dBm, well, 60 dBm, 60 dB equals 10 log something. What is that something? 60 dB? Anyone? 10 log of 1 million is 6, times by 10 is 60. So 60 dB is equal to a factor of 1 million. Okay. Which means that 60 dBm is a power level which is 1 million times larger than 1 milliwatt. That's how we interpret that. 60 dB relative to 1 milliwatt. 60 dB is a factor of 1 million because log of 1 million is 6, times by 10 is 60. So what is 1 million times larger than 1 milliwatt in watts is 1,000 watts, because there are 1,000 milliwatts in 1 watt, and therefore 1 million milliwatts in 1,000 watts. Can get confusing. 60 dBm is the same as saying 1000 watts, which is the same as saying how many dBW? $30 dBW. Because dBW is relative to 1 watt. 1000 watts relative to 1 watt is a factor of 1000. Convert to dB, log of 1000 is 3 times by 10, 30. So these three values are exactly the same. 1000 watts equals 30 dBW equals 60 dBm. In communication systems, we often see all of those units used. dBm for decibels relative to a milliwatt, dB watts, dBW, and simply watts or milliwatts or whatever prefix we want. So be aware of what they mean, especially dBm and dBW, and how to convert between them. Because often in questions and in devices, when you buy a device, it'll be expressed in dBm, not in watts or milliwatts. If you look up the specifications of wireless LAN access point or your laptop or even your mobile phone, the receive and transmit power will most likely be expressed in dBm. In one of the handouts at the front of your notes, the handout titled Definitions and Concepts, on that last page there's the definition of dBm and dBW. So at the start of your handouts you'll see that written down.